first talk will be by Ćavar, right? And
he doesn't hear you, I guess.
I think he hears me. Do you hear me?
Yeah,
he does. Okay, I'll be sitting here and I'll show you when it's 5 minutes before the end of the talk. Okay?
Okay.
All right.
So just stop me if you don't hear me or something goes wrong with the technology. I will switch over to the slide mode. I think that Adam decided to share the slides as Google Docs and as PDFs. I was thinking that I could give you the access to the Google Docs so that you can leave comments and notes on the slides. Then I thought if Adam is linking that to a public website, everybody can do that, and this would be a little bit odd on the long run. So if you want, and I would appreciate that, I could share those with write permissions with you, and you could leave me notes on the slides later. This is an unusual talk I see with respect to the rest of the program because there's not much of fancy research in linguistics here that I'm reporting on. It's more engineering and technology stuff that we were working on, implementations, trying to re-implement something like an LFG parser and various other parsers. And I'm grateful that you allowed that to happen at this conference. What I wanted to report on is the work that I was doing over the last year with some of the grad students here at IU. And it has sort of a longer history over the last decade or so. I was always asking people, why don't we develop a new parser? And I was talking to Ken and various other people, Ron Kaplan and Gerald Pan, Richard Strout, and so on. And some people would just tell me that this is completely nuts, I shouldn't do that, it's too much work, and we wouldn't manage to get to it, and so on. We nevertheless still started, so we're grateful for their support and comments over the last couple of months with some work. We asked over the list some time ago whether people would share with us some grammars and implementations of different languages, and we got material from Mary Dalrymple, and we got the Norwegian grammars and access to the Polish ones and so on. And those were very helpful actually for us to see whether our parsers, what we implement, actually can process these grammars and implementations and so on. We worked also a little bit, and we still work now with Larry Moss with ideas how to implement certain types of semantic calculi in something like an LFG or any general type of lexical grammar framework, like CCG, for example, as well. And he's supportive of this entire project here of redeveloping some parser environment and grammar engineering platform. And of course, the local colleagues here, like Sandra Kübler and Markus Dickinson, helped us a lot. And some developers of tools that we use helped us as well by correcting errors and mistakes in their compilers and technologies. And I will explain a little bit about that in a second. The motivation for this parser was basically that we felt that we need something like a modern grammar engineering platform, modern in the sense that the old XLE with TickleTK interface and so on didn't sort of seem to be very attractive and useful for us. We wanted to have some more, some fancier tools and technologies around the grammar engineering platform. And we wanted to have a system that is platform independent, that we could also use not just on Linux, OS X or Windows, but also on Chrome OS, Android or iOS devices. For example, taking mobile devices to the fields and working with grammars and morphologies while documenting languages somewhere abroad. We were also interested in technologies, in parsing technologies that would be parallelizable, parallel processing on multiple cores or CPUs, or that would be distributed in their architecture so that we could spin off computing intensive processes over multiple devices. and so on. For that, we would need a completely new architecture. I don't know anything about XLE really, actually. I didn't have access to the source, so I can't tell you whether this is parallelizable or whether actually maybe it is already internally threaded and parallelized. I have no idea. It was also crucial for us to develop something that is interoperable so that we can tie it with scripting languages, with web languages, like Python or JavaScript, for example, that we can import and export standard exchange formats of grammars as well as analyses, tree annotations, and so on in XML or the JSON formats and others. The core problem that we had, why we decided last year to just say, okay, we have to start redeveloping that ourselves, was that we actually couldn't get the license from Xerox for XLE, and this had to do with state laws in Indiana that forbid contracts that require that the legal disputes would have to be sort of managed in the state of California. It would have to be Indiana, and Xerox refused to accept Indiana, and we didn't get the license altogether, so we said, okay, it's time for a redevelopment, and we need to get something that is really truly open, and we were favoring the Apache license 2.0 license that would give us the opportunity to work also with commercial, with industry partners. In the same way, some of them do not accept the GNU license, like Google, for example, or maybe even Nuance, I think. So we decided to develop something that we can distribute under the Apache license. And for us, the goals were basically, we were interested in language documentation mainly, and using computational tools, developing grammar engineering environments so that we can document languages in depth, going beyond what is typically done in language documentation work, which is recording, transcription, and extraction of specific linguistic information about the target language. Previously, we were using XLE for research and education, and as I mentioned, we can't use this at IU, so we need a platform, we need something where we can sort of teach grammar engineering in computational linguistics here at IU, and this is one of the goals. And of course, we were interested in a tool that would allow us really to develop real applications that we can deliver to even maybe industry and project partners and so on, something that generates robust parsers, technology from the technology perspective, not necessarily robust grammars or something like that. And we were also basically working on something like what I would call a merger between white and black box modeling. So white box modeling I consider grammar engineering, and black box modeling, something like machine learning, neural networks, and so on. And so far, we thought that there is no platform really that brings these together, where machine learning algorithms could enhance grammar engineering, or the other way around, grammar engineering and knowledgeable feedback can improve machine learning algorithms. And this is what we wanted to experiment with. We created an infrastructure last fall. Basically, we created 2 Bitbucket repositories. One is basically the secret one where some of you are members. If you want to get access to that, you can just write me, send me a mail, and I will share the repo with you if you have a Bitbucket account. It's a repository that we call sort of the shameful repository, where we have all kinds of hacks and experiments, a lot of small sub-projects where we implement morphologies and test them and parsing algorithms and so on, something that we wouldn't necessarily want to expose to the outer world and to experts because it's not professional really. And then we have an open repository. We just set one up, but we didn't copy anything over yet. We'll do that in the next weeks over the summer now. Some of the ready algorithms that I will now report on what we have. We started designing a platform, so it was took us a while to figure out what is the best environment for development of such a thing, such a parser, and we decided to use C++11 or newer, so C++14 is also possible. We used the GCC environment and CLang environment, the LLVM, on Linux and Macs, and on Windows we used Cygwin so far, but we started experimenting also with compiling the entire platform, the algorithms on Microsoft Visual Studio, so we get native code for Windows as well. We use a CMake-based compiler configuration, which is very efficient and minimalistic, so to speak. We don't have to bother about complicated make files and stuff. We use the BNFC, which is a BNF converter tool to convert BNF grammars to code. The BNFC is a tool written in Haskell, and it generates Flex and Bison, so Lexer and parser generator compiler code that then gets compiled to C or C++, for example. I'll explain this a little bit more, why we use that and how. And we document the code using Doxygen guidelines and compile them the documentation using Doxygen directly. As I mentioned already, we use Bitbucket. It's similar, or it's actually equivalent to GitHub. It's just an accident that we use Bitbucket because they offered themselves to give us unlimited access for resources and projects and so on. For development, we decided to use the CLion IDE, which we get for free basically as students and professors. There is a free academic license for the professional version, and it's one of the better C development environments from my perspective. But since we're using CMake, there is no reason why you have to use any of that. The projects that we generate for the different tools and components of the parsers and algorithms are all basically predefined as CLion projects, but we can also use the command line and just start CMake and compile the tools straight away. Use any kind of editor. And we try to compile and develop the tools at the same time on Linux, Mac, and Windows, so that we see that it's always platform independent. In the current version, the requirements are we basically just use the C++ standard library so far, and some of the Boost libraries for regular expressions, for example, and so on. The Boost libraries are just basically something that the C standard library should contain, maybe one day will contain. Very useful tools and extensions that make programming in C++ much easier and pleasure. We use FOMA for morphologies. The XFST compatible, I guess that it's completely compatible, I'm not certain about that. Morphological compiler, finite state compiler. In the final version, we experiment now with OpenFST and OpenGram, Thrax Gram development tool. That both tools are developed mainly by colleagues at Google Research. They are C++, these are C++ libraries. OpenFST is a weighted finite state transducer library in C++, and OpenGram is actually on top of OpenFST, on top of the weighted finite state transducer library. There is a single stack and a dual stack pushdown automaton that would allow one to model context-free and even context-sensitive grammars and parse those. We optionally experimented with libraries that we can plug into the parsers, alternative tokenizers, for example, Ukto, the Unicode tokenizer, which is a rule-based tokenizer that comes with rules for a couple of languages. And we also looked into alternative finite state libraries like the Helsinki finite state technology, transducer technologies, and so on, to optionally link them into the code if people would desire that. We don't see a use for us right now for that, but it's definitely possible to have this like a module in the environment. All these technologies are implemented and available as C or C++ code, so it's very easy to actually add that to the system. What we thought about was that we actually develop a library of services and algorithms rather than a monolithic parser or tool set for grammar engineering. And so we started collecting algorithms to parse context-free grammar formalisms. We designed our own type of PCFG or CFG formalism that is compatible with the XLE LFG type of context-free backbone. We wanted to parse XLE grammars, be compatible with that as much as possible, use XFST compatible morphologies based on FOMA, be able, what we were thinking of, to convert XFST morphology outputs to various formats for various other grammar formalisms, for example, lexical rules or representations for categorical grammars, just translated out of the XFST morphology outputs. And then the tokenizers that we used, some were based or are based, say a little bit later, on FOMA as finite state transducers. Some are rule-based tokenizers as delivered by UCTO. And we just implemented some regular expression-based tokenizers, white-space tokenizers, and so on for last resort if the language doesn't have specific rule sets. And then parsing algorithms that use the different formalisms above, like context-free grammars, PCFGs, and so on. And the advantage of that is basically, in addition to that, we wanted actually to relate some of the grammars and parsing algorithms and outputs to dependency trees and analyses to be able to compare dependency parsers with deep grammar outputs, so we could map, for example, C and F structure outputs onto dependency relations and compare our parser then, for example, with the Google engine. We also wanted to integrate training and machine learning algorithms to be able to use a probabilistic grammar backbone, also probabilistic morphologies, and probabilities over C and F structure relations as described in some papers, for example, by Mark Johnson or earlier by Ron Kaplan in some talk a long time ago at some LFG conference. To sort of experiment with probabilistic LFG and related formalisms. And of course, the entire source should be available as C++ code base, and we could from that compile modules for common scripting languages, for example, for Python. If we have such a library, the idea is that we can then experiment with different architectures, with the classical pipeline architecture where we tokenize, morphologically analyze, parse, and then process the semantics, or where we have something what Jakendorf suggested in his book, The Parallel Architecture, and then recently in a paper, parallel processing, where we are basically just mapping in some blackboard or message passing architecture the representations from different linguistic levels, rather than having a pipeline architecture. And in this parallel architecture, there would be also a possibility to describe mapping relations between phonological representations and semantic ones, and so on. None of that, of course, is implemented. The only thing that we implemented so far is just the basic pipeline architecture. But we are working on the concept of something like Jakendorf's architecture, the parallel architecture. And so the components that we built so far, of course, as I mentioned, tokenizers, trivial, simple space-based tokenizer regular expressions can be used, boost algorithms are underlyingly used for that. We have FOMA-based tokenizers, in particular for Burmese and related languages. One of my collaborators here works on Burmese and Hmong and so on. We tested that we can link and use the UCTO-based tokenizers, but we never tested those really on real languages. This we can do, and this exists. we use for morphological analysis FOMA, and we developed so far our own type of English morphology because we couldn't get anywhere in English morphology, so we started developing one ourselves. A long time ago, I developed a Croatian morphology using a completely different framework based on a compiler called Ragel or Regel or something like that. And I'm translating this now to a FOMA-based or XFST-based morphology for Croatian. And Ruben is working on Burmese, and one of my PhD students is implementing Mandarin. Not much of a morphology there, but we're basically developing the entire lexicon using the finite state transducer with feature outputs and so on. This type of implementation we tested. So here I tested that on an Intel i7 CPU with Windows, and we get something like 200,000 ambiguous tokens per second analyzed in the implementation that we have raw from the FOMA library. So this is very efficient. On the Linux implementation, this can be increased by 50%. So we could get really something like 300,000 tokens in a second. Tested on the most recent Fedora with new GCC 6, I believe. Then what we were thinking is that now in this architecture we can integrate actually also common part-of-speech taggers easily. If there's a missing entry in a morphology or lexical items are missing there, we could use part-of-speech tags, for example. We didn't test that. This is just a potential direction in the future that we do that, open this up for alternative tools and components. For the syntactic parsing, we implemented the first simple early type of algorithm that just basically uses hash tables for rules and edges, just prediction, scanning, completion, classical type of algorithm. The edges are just indexed dotted rules indexed over the input tokens and stored on the chart or stack. In this parser we didn't do that. We implemented a small unifier, but we didn't implement the feature representation yet. I'll say a little bit after in the next slides about that. So the idea there would be to use what was suggested in the literature, that one should basically unify over the final trees that the parser outputs. This type of architecture has its limitations. It's simple and efficient. I think when we tested that one, just to parse, we got something like 3,000 structurally ambiguous sentences with an average length of almost 5 words per sentence, and something like 2.5 ambiguous trees per sentence output. This process can be processed with tokenization and morphological analysis in less than a second. 3,000 sentences on the normal CPU on a laptop. So this is very efficient. Of course, now if we would unify, this will be much more complicated. But what we wanted to do is introduce, for example, the possibility to have probabilistic backbones. So we could have, for example, for an LFG, not just a context-free grammar backbone, but actually a probabilistic context-free grammar backbone. Or we could represent the parsing as something like a chain of symbols, as in the Markov chain over the right-hand side symbols if we are parsing in a bottom-up parser. So the famous, you probably all have seen that, the toy grammar rules. We represented them in a weighted finite state transducer now by parsing them into a finite state representation. We can skip over that, but basically what we do there is displayed here in the graph. We represent, for example, every edge has every transition has 3 components: an input symbol, an output symbol, and a weight. In this case here, all transitions in the graph have the weight 1, so they are basically neutral. equivalent to no weight at all. The small e's are epsilon transitions, and there could be an epsilon transition and an epsilon output on the transition, and we represent the right-hand sides as input symbols, in this case here, and the left-hand side of a context-free rule is then an output symbol. So you see that on the right side, from state 3 to state 4, if your input symbol is the VP, the output symbol is an S, and preceding were an optional and an obligatory NP input. So we can represent context-free grammars this way, and this is our grammar representation now. And easily now, in this case, this would be for the purpose of a button-up parser. We could revert the input and output and use the same representation for top-down parsing. The algorithm that we used for that weighted finite state transducer representation is just the common early algorithm as well. So we have a lexical initialization phase where we use the output from the morphology and generate initial edges for the tokens that we have processed. And then we recursively send those edges through the weighted finite state grammar or transducer, and this generates new edges, and we continue with this loop in the early fashion until there is no more new edges or until we end up in the recursion that we recognize and we stop. And then we read out the completed edges with our root symbol or target. The edges here, in this case, we implemented as they're just integer tuples. This is the indexes over the input tokens as a vector and the state in which the edge is in the weighted finite state transducer, plus, I didn't mention this here, a history, so we keep track of which two edges in combination are responsible for creating a new edge, so that we can backtrack and reconstruct the tree, the parse tree. So these are just back pointers. All nothing new, all standard and classic. We implemented that as a class on our own in C++. It's somewhat slower than the simple early parser. Somewhat, actually 50% slower or even more slower. But what we get as an advantage now is, and I mean the slower part is definitely due to the way I implemented that, there is a lot of potential for optimization and improvement of the algorithms for the parsing and search algorithms through the parse and so on. But what we have now is a possibility to represent probabilities of rules, for example. So a path through a machine could correspond to the probability of a context-free grammar rule. Or we could treat the transitions over symbols, the right-hand side symbols, for example, in the bottom-up parse, as in the Markov chain, and just consider sort of the probabilities transiting from an NP to a VP and stuff like that without ignoring the rule as such. We could also treat the weights as actually feature structures, ADMs, and as unification functions. Weights are very abstract in weighted finite state transducers. They could be in principle implemented in C++ as an object that does anything, whatever you want. It could be a combination of PCFG type of probability calculations, Markov chain type of probability calculations, and unification functions as well. And we didn't implement any of that complex stuff, but this we will do when we switch over to OpenFST as the backend for weighted finite state transducers and get rid of our old implementation. We implemented something like an export of dots so that we could visualize the grammar as a graph. We could convert this now, of course, to a SVG, PDF, or PNG graph. We can binary dump the weighted finite state transducer for faster load cycles, for example. If we would use the OpenFST, we would benefit from a much richer set of library functions. Optimization, for example, I implemented just the basic minimization of the finite state transducer, and I didn't implement at all any type of epsilon removal operations that the OpenFST would have, for example. I would have a full minimization function implemented as well. And if we would then switch over, and this was what we started discussing with Richard Sprout, to OpenGRM, we could maybe transfer the entire grammar to a weighted finite state transducer-based pushdown automaton with one or with two stacks, and experiment with higher level complexity with mildly context sensitive grammars or something like that. We didn't do yet anything about that, we just sort of were philosophing about that. One of the reviewers mentioned that in the review, and we discussed that here ourselves as well actually, we could now of course say we would limit the recursion depth, for example for standard embeddings, and this way map the entire context-free grammar onto a real weighted finite state transducer or a normal finite, just a deterministic finite state transducer, and optimize this way and get extremely fast parsing. We can also dump this as raw C code and compile it into a standalone, very efficient, fast parser that would then have a limitation on the recursion depth. But this would probably not matter on the long run for most of constructions. The underlying the formalisms, the grammars are written in some formalism, of course, and we use for that the BNF tool, the BNF converter, which, as I mentioned, is a Haskell-based tool that generates from BNF grammar definitions code for C++, C, Java, Python, and other languages. And we implemented the CFG formalism that is similar to what the XLE tool backbone supports now. The PCFG formalism adds to that just the probability for each rule. So if we would extract context-free grammar rules from a tree bank, we could count them and route-wise them and have a probability estimate that we attach to the rules. We have a parser that does that, and we could read that in and represent this then in this weighted finite state transducer. And we worked hard on parsing all the XLE components, the config section, features, lexicon, morphology, and so on. So far we didn't finish the templates yet, and this is a problem, so we need to finish the templates and the features and the morphology and so on to be able to finally find a representation of all the features and lexical entries, a feature structure representation that we can then correctly unify and experiment with unification algorithms. This is what we're working on right now. When I say incomplete here for features, lexicon, and morphology, for example, this means that we are above of toy level parsing. So we parse actually almost everything of these specifications, what we have extracted from the documentation that we could find, and what we have found in the implementations, in the grammars that we got. The Norwegian grammar or the Malagasy grammar, for example. There are still some problems, and some components are missing. The rules we can parse. We are not parsing edit rules. We are not parsing meta rule macros yet, and so on. So this stuff has to be added. We also have to differentiate between parsing as mapping, analyzing the syntactic structure and mapping it into some internal representation, and basically the semantic processing component. So for a lot of that, we didn't finish all of the semantics yet. I'll show you an example. Here's just a small chunk of what is it here? Can somebody tell? Is it the features section of a BNF that represents or lexicon section actually that represents the lexical entry. And what you see here is the labels, Bacchus now form grammar formalism. So we specify like what comments look like. Here in this case in XLE there are double quotes, opening and closing, and there is a specific list notation, square brackets notate lists of certain things, and then you have to say what the delimiter or terminator for this is, and so on. This is a basic example of how we implement the grammar formalism, and this is the output. So what BNF generates is a skeleton class for a parser, and all labels that you see here on the left side that are terminated with a dot represent actually methods in the C class that are visited once this rule is parsed. This way you basically implement the semantics of what that happens directly in this code that you see here under the code for rule as goes here, for example. And this we didn't do for a lot of these components of XLE, but for the rules, for example, we did. The BNFC converts to C++, so it can convert to other languages as well, which is an advantage now. So if we define fully now the XLE formalism, we'll be able actually to generate parsers in all kinds of different languages. And in addition to that, we can generate, for example, Python pigment definitions that allow us to have a nice editor that is doing syntax highlighting for XLE formalisms and stuff like that.
Damir?
Yes?
We need to have some time for questions. I don't think you saw my signs, but we're out of time. So
Oh, we are?
yeah.
Oh, let me just give me a second, yeah?
Just a second, and then we'll have 7 minutes for questions.
Oh, okay,
Okay.
good. Just quickly then. Okay, so we started with unification. Unification implemented as a directed acyclic graph. There is no implementation of anything like disjunction, constraints, and negation, and so on yet. But this is because we didn't finish actually the entire feature representation of the XLE grammar formalism. And the to-dos are basically, so far we are using on Windows Cygwin. We are trying to compile that to native DLL so that we don't need any Cygwin installation on Windows. On Mac OS it's similar, it's much easier to compile actually the libraries, but it works, we can run it. And we want to create all these libraries and then basically be able to create something like an editor and a platform. For example, just using plain Python and Qt, PyQt, for example. We don't need to program the entire grammar engineering platform in C++ if we use the libraries and interface with other languages that allow us to do that nicer and easier. We have to finalize the grammar parsing, and we hope that somebody will help us. There are a lot of issues with the syntax, but in the end we do not understand fully the semantics of certain notations in different sections of the XLE grammars, and we'll have to maybe utilize the LFG list and ask people for help, and so on. And there's a lot more to do, of course. That's it. Thank you. I'll switch over to face mode.
We have about 7 minutes for questions. Yeah, Tracy?
Hi, Dummer, it's Tracy. I actually have a stack of questions, which I'll start down them, and if other people have questions, they can go. So I think one thing people here would be particularly interested in is, what's the ownership model if someone uses this to, say, develop a morphology or a grammar, which then perhaps they want people to use it for research, but maybe not for industry. How's that work with the license you've chosen?
Well, the code is published under the Apache license, so whatever you do with the code or with any grammars or derivatives of that is your thing. You can share it if you want, you don't have to. You can hide it. It's not a GNU license.
Okay, something else. One of the things I think that both the LFG and HVSG communities have been able to really exploit with this style of grammar is the ability to do both generation and parsing. For example, if we're using it in MT or sentence condensation. You spoke, call grammars. You spoke only of parsing direction. What are plans in the long run for generation?
Of course, I know. We didn't think about that at all, I can tell you. I mean, we can easily work with the architecture also in a way to use it as a generator. It's just that we actually didn't give it a thought at all. So far, it was just about parsing. And I think that, I don't see a big problem actually to do the reverse using the architecture we experimented with. And there is a lot of flexibility actually to revert that. I mean, if we base everything on the long run on something like a weighted finite state transducer platform, shouldn't be such a big deal.
Still me.
Other questions?
Oh, another one.
I have,
Okay.
that's it.
What do you do one?
Hi. I have just a question about your tokenizer. You are using FOMA and Octobase for tokenizing Tibeto-Burmese languages. And I wanted to know what kind of results you have, because usually this kind of languages, the tokenization is treated as a structured prediction problem. And like for example, Christopher Manning and Andrew Ng, I don't know how to pronounce his name, they published results on segmenting, for example, Burmese and Chinese using conditional random fields or long short-term memory recurrent neural networks. And they are very good results, and I wanted to know what kind of results you get with the rule-based tokenizer for this kind of languages which have no word boundaries, which can be easily detected.
If I understood correctly, the main question was about how to tokenize these languages that we are dealing with, like Burmese, for example.
Exactly.
He wants your results. He wants your results down there.
Oh, the results. Yeah, I couldn't wake up and win to stand up here with me at 3:30 in the morning. But we should put some results on the Burmese. I think he had a paper. Where did he submit this paper? Maybe at the LSA. This January, so he will report on the results. It's a lexicon-based system, so basically you just implement something like a morphology in FOMA, and it splits the input into sequences. I guess as good as your lexicon and collection of morphemes is, as well will your segmentation then be a tokenizer. So far, I don't think that he experimented with anything that is probabilistic in any way or goes beyond that. I can't tell you. I didn't evaluate that part. I don't know Burmese.
Okay. I will advise you to tell him to read about these results, because I think you will get better results for these types of languages.
Yeah, I mean, in principle, actually, we are not opposed to having any kind of, we could use neural networks and we could use statistical methods and we can plug them in here. This is actually why I'm saying that we are developing such platforms where we can do that. Whether these methods, statistical methods are better or whether there are any other, I don't know. I have no idea.
Hi, Donner, this is Ron. So I'll make a comment about that and then I'll make another comment. So when you think of tokenization in isolation from all the other sources of information and constraint that you have in the full pipeline or full grammatical system, then you're attracted to these particular statistical approaches, and you measure them independently, and you get good results. But those may not be the right results by the time you take in all the other constraints for all the other modules. So, what's more important maybe is the ability to integrate before you do these statistical selections, no matter how well the statistics is doing by itself. So that's one comment. Another comment.
Just 1 minute left. We have just 1 more minute left.
So does somebody else want to?
No,
No,
go for
it's
it.
okay, maybe if you want to reply to your first comment.
Yeah, you can talk. Okay.
Sorry.
No, I understand you're suggesting that a combination of, a hybrid combination of statistical and rule-based systems is probably fruitful, if I understood you correctly. The sound gets bad over here to me, actually, from I believe that. I mean, I didn't see, we didn't evaluate anything yet. We're just coding that and we are engineering that, and I don't know, we'll have to see. Hopefully we have some platform and something to play with and evaluate all kinds of language material. This is what we are trying, and we are collecting now Chinese, we are collecting Burmese, many other languages as well, actually, and trying to code morphologies. I didn't mention that, but beyond all that, what I mentioned, there are more languages that we are dealing with right now. A lot are languages that are coming from totally unwritten or undocumented. We were working with Chitino. We are trying to write down a morphology for Chitino from Oaxaca, Mexico, and so on, which is highly complicated stuff. And maybe a combo, a hybrid system using tools that are statistical and rule-based will be sort of the solution. On the long run, what I want to sell is basically white box modeling as the solution anyway. I'm not the statistical linguist, whatever. So,
Okay, thank you very much.